Welcome back to week 4. This week we'll be covering chapter 27 on color. So this chapter, chapter 27, covers color in our world, selective reflection, selective transmission, mixing colored light, mixing colored pigments, and then a few questions about why things look the colors that they look. So first of all, color is an experience that's unique to the person seeing. So it's how their eyes perceive colors. Everyone doesn't see colors the same. And it depends on your eyes, and it depends on also the light that's reflecting into your eyes. So for example, if you were to look at something with a fluorescent light, it might appear very different than when you go out in the sunlight and look at that. And that could be like this lady looking at her makeup color. Sometimes clothes you buy in a store, they look one color in the store. They look completely different when you get out of those fluorescent lights. Now the color that we actually see depends on the frequency of light. So the lowest frequency that we can see is perceived as red. Below that, which we can't see, would be the infrared. And then as you move up in frequency, you go red, orange, yellow, green, blue, up to violet. So the highest frequency that we can see is the violet. And then beyond the violet, which we cannot see again, is the invisible ultraviolet light. Next up, we'll have a video on the frequencies of light and what colors of light we see best.
The sun beats down, emits light. Why does the sun emit light? Honey, those electrons in that sun are shaking like crazy. All kinds of frequencies, okay? And so what you get is you get all kinds of frequencies of light coming down to us. And if we made a graph of the frequencies of light versus the brightness, we'd get something like this. We get something like this. Over here you can't even see. That's the infrared. Over here you can't see. That's the ultraviolet. But it turns out that right in here, that's the frequency of light that that is emitted mostly by the sun. And that's right in the middle of our color spectrum. Because we start down here with red, orange, yellow, green, blue, violet. And guess what's right in the middle, gang? Begin with a G, end with an een. Try it. Excellent. All right. Green. It's green. Green's right in the middle. Turns out a yellow-green. A yellow-green is what the sun emits mostly. It's like a chartreuse. When I was a teenager, honeys, I had a chartreuse convertible. You could see that thing 15 miles down the road. Okay? And you know why you could see it so well? Because most of the light from the sun is that color. And guess what we have evolved to see best of all? Take a guess. Yellow-green. We used to call it chartreuse.
So they paint fire trucks that color these days?
Did you notice that, Paul? What are the new fire trucks? They used to be red. What are the new ones? Yellow-green. Why they be yellow-green, honeys? Huh? Why? Because you want to see those things coming down the road. And so they finally said, hey, let's paint them the color that human beings can see the most. Yeah. You notice the color of your street lights? What color they be, gang? Yellow. Yellow, little greenish, little yellow-greenish, mostly yellow, right? Why the street lights yellow? They used to be incandescent lamps that used to glow white. Now they're making them yellow. One strong reason has to do with, guess what we can see most? Yellow. Let's suppose you got a 100-watt lamp, and it's white. And you're seeing that a lot of this is coming out, and a lot of this too, right? So you're spreading along all that, right? Let's suppose you got 100 watts only of this. How about your eye, honey? You're going to see more light because it's hitting right where you can see best. Now, those yellow lamps aren't very good for your complexion and that sort of thing, all right? But when you're driving at nighttime, you're not into that. You're into what's on the road. You really want to maximize seeing. And hence, that's one strong reason for the yellow-green lamps and the yellow-green fire trucks.
So as you just saw in the video, the distribution of solar frequency is uneven. So the most prominent frequency given off by the sun is the yellow-green region. So this region in here, that chartreuse or yellow-green. And this is where our eyes are most sensitive. So that's what we're picking up the most because that's what most of the light given off is. Let's do a review question. What color can the human eye not see, or what frequencies can the human eye not see? Can we not see infrared radiation, ultraviolet radiation, both of these, or neither of these? The answer is both. We cannot see infrared radiation and we cannot see ultraviolet radiation. Now, selective reflection means that we see the color of something by the light that it reflects. So we see whatever is reflecting off that surface. Now, objects reflect light of some frequencies and absorb the rest of the frequencies. So, for example, a rose petal absorbs most of the light and reflects the red. So on a red rose, that's why we see red, because red is being reflected. Objects that absorb light and don't reflect any light appear black. And objects can reflect only those frequencies present in illuminating light. So it can only reflect the colors of light that's coming into it. So if you were to only have a red light shining, it can't reflect green light. It can only reflect what's going in. Now, the color of a transparent object depends on the color of light that it transmits. So, for example, the reason that we see blue glass as blue is because red, orange, yellow, green, and violet are being absorbed, and the blue light is the only light that's going through the glass. And so we see the glass as blue. So in your eye, you actually have three primary color receptors. You have red, green, and blue receptors. And the radiation curve, as you saw in the video a little bit ago, is divided into those three regions. So if you were to map the frequency down here or graph the frequency down here and graph the brightness up this way, as you follow that curve, this region here, the lower frequency is red, green, and then blue. And our eye mixes those primary color receptors together to get all of the different colors that we see. So, as I mentioned, when we take our primary eye color receptors, and you could do the same thing by shining lights, you can mix these colors together to get all of the different varieties, depending on how much of each of these lights you have, to get every different possible color. And when you add all of these, red, blue, and green together, you end up with white light. Now, if you'll notice, these mixing of colors that you see with your eyes is not the same of like when you mix paint together. So I don't think anybody mixes red and green paint and expects to get yellow, but that is what your eye does with light. So it is a little bit different with light mixing colors and how we perceive those colors being mixed. Just like you don't mix all the colors of paint, you don't pour every paint together and think you're going to get white paint. So the light mixing is different than mixing colors, say with crayons or paint. So you can see from the diagram that when you mix red and blue light, you're going to end up with magenta. When you mix red and green light, you'll end up with yellow. And when you mix blue and green light, you'll end up with cyan. Okay, so up next we have a video on mixing of light colors.
Hi gang, color physics. You see me in full color, not because of a white light shining on me, but because of three lamps. A red one, a green one, and a blue one. And all these three colors mishmashed together to give the same effect as white light. Let's look at these one at a time. Put the red lamp on, and I have a shadow. Of course, the shadow is black because no light's hitting there. Let's try two lamps. That black shadow turns out to be green because now we have green and red shining. And the green lamp casts a shadow which is not black but is red. That's because a red light's hitting it, huh? Let's try three lamps, red, green, and blue. Now we get three shadows. This is no longer green, it's greenish blue. This is no longer red, it's reddish blue. And this is yellow. And yellow turns out to be the average of red and green. And if I overlap these, I can get all kinds of nice colors. And bear in mind, all these colors you can see are the result of only three colors, red, green, and blue. Those are the colors of your TV set. TV physics. Physics all around you. Yay.
So when red, green, and blue light overlap, what do you end up with? Red light, green light, blue light, or white light? And the answer is white light. So mixing all those primary colors of light, again, different from primary colors of paint, when you mix the primary colors, you end up with white light. When the color yellow is seen on your TV screen, phosphors being activated on the screen, what are they? Are they yellow, blue and red, green and yellow, or red and green? The answer is red and green in light mix to make yellow. A blue object will appear black when it's illuminated with what colors? Blue light, cyan light, yellow light, or magenta light? The answer is yellow light. So let's try another review question. A red rose will not appear red when it's illuminated only with red light, orange light, white light, or cyan light. So which one of those colors does not have red in it? The answer is cyan light. So cyan is a mix of blue and green light. So if you don't have, again, red light going into something, then red light can't be reflected and you can't see the color red. Now, mixing colored pigments is probably more what you naturally think of when you think of mixing colors. And we've all been taught that the primary colors are red, yellow, and blue. And as you can see with mixing colors of ink, like in a color printer, if you've ever looked at that ink strip, you have the kind of magenta, yellow, and cyan, so sort of the red, yellow, and blue primary colors, which mix together to produce the color that we would normally think of the image being. When they add some black to that to get the different lightnesses and darknesses in the picture, that's when you end up with the full color photo that looks like how we think it should look. So as I mentioned before, when we mix colors of light, we get different colors than what we think of as when we mix like pigments, like paint. When we mix colors of lights, we call that additive primary colors. And again, those primary colors were blue. For additive primary colors of light are blue, green, and red. Now, on the other hand, when we mix colored pigments, we call this subtractive primary colors. It's essentially the opposite of the additive primary colors. And the primary colors, the primary subtractive colors for pigments are cyan, yellow, and magenta. And so, as you typically would think of, when you mix all the colors, you get black or something very dark. When you mix red and blue, you get purple. When you mix blue and yellow, you get green, and so forth. So this is mixing colored pigments again, which we call subtractive primary colors. So for example, when white light passes through overlapping sheets of all of these colors, all of the frequencies of light have been subtracted and we get the color black. When you have, if you were to look through cyan and yellow sheets and overlap those, all of the frequencies except for green are subtracted, and that's why we see green. So various proportions of cyan, yellow, and magenta dyes will produce nearly any color in the spectrum. Again, for subtractive primary colors. So next up, we're going to look at a video clip on why the sky looks blue.
Did you ever be wondering why the sky is blue? How many say, well, it's probably the reflection of the water. All right, now go to Minnesota. Now go to Kansas. What's the color of the sky in Kansas? Well, it's usually a yellow-green, right? Come on, what is it, gang? It's still blue. Why is the sky blue?
It's absorbing all the red.
Little bit different phenomenon going on here. Let me just tell you about it. It turns out that light coming down from the sun, boom, showers itself upon the atmospheric molecules. Now we got big ones, we got little ones, we got all sizes up there, okay? And these molecules will scatter off the frequencies of light. It's called scattering. Now, what frequencies will be scattered? Let me give you an example. Let's suppose I have a couple of bells here. Here's a little bell, and here's a big bell. When I disturb these things, they're going to scatter sound off in all directions, and what will the sound be, high pitch or low? Let's try the little one right here. Boom! You hear that? Now let's try the big one. Bing! Did I have that right? No. How many say no, I got that wrong? Wrong? Okay. No, that's completely wrong. It turns out the little bell will bing, and the big bell bong. Isn't that true? Guess what behaves the same way up in the sky? The what? Molecule. What do you suppose the little tiny ones will ring? High frequency or low frequency? High frequency. How about great big ones? Low frequency, okay? Now, what are the size of the molecules in the sky? Large or small? Begin with a S. Small. And then nitrogen and oxygen mostly. Isn't that true? O2, N2. And when that sunlight comes beating down on those things, it scatters off. Light scatters off. And it turns out the color of the sky is the color of all those little bells, or all those little optical tuning forks, or all those little vibrators. And they're vibrating at mostly what frequencies, gang? High frequency. How many know what high frequency looks like to the human eye? Blue. And higher frequency, even violet. Let me tell you something. The sky really scatters off more violet than it does blue. But you know what? We're not so good at seeing violet. We're a lot better at seeing blue. So guess what our eyes tell us the color of the sky is? Begin with a B. You could have done that without the hint. Okay? And it's blue because the tiny, tiny particles are scattering off the high frequency. So we see a blue sky. Okay?
So just to recap, all those tiny, tiny particles up in the atmosphere are emitting very high frequency light. And so the tinier the particle, the higher frequency of light that it will re-emit. And again, it emits more violet than blue, but since our eyes see blue better than violet, we see the blue color and not so much of the violet color, but we see a lot of blue, and so we see the sky as blue. Now, the exact color of blue that we see in the sky can vary depending on the conditions of the day. So on a clear, dry day, we're going to see more of that blue come through, and we'll see a much deeper blue sky. On a clear, humid day, you'll see more of a medium blue sky. A little bit of that blue will be reflected off and not, or absorbed and not be seen. And then if there's lots of dust particles and larger molecules, the nitrogen and oxygen in the atmosphere, then you'll see less blue and it'll have more of a whitish appearance. After a heavy rainstorm and it washes away all the airborne particles, then you would see a deeper blue sky again. Let's do a review question. A white sky is evidence that the atmosphere contains mostly small particles, mostly large particles, a mixture of particle sizes, or pollutants. The answer is a mixture of particle sizes. So you're seeing lots of different colors of light being reflected, and when you add all those different colors of light together, you get white light. Next, we're going to look at why sunsets look red. So light that is the least scattered is the light of low frequency, and these travel best through the air. So these are things like red, orange, and yellow at the low frequency end of the spectrum. Now, when sunlight comes into the Earth at noon, it's getting the shortest path, and so all of that blue light has not been scattered too much, and so we're not seeing those low frequencies of light. We're seeing the blue predominating. As you get to sunset and the sunlight is having to travel further and further and further, more of that blue light gets scattered, and only the low frequencies, the reds and oranges and yellows, are getting through. So a variety of sunset colors is evidence for a variety of elements in the sun: apparent atmosphere thickness, atmospheric particles, or primary colors. And it's atmospheric particles. So as that sunlight travels through more and more particles, that blue light will get scattered, and what's left is that little bit of low frequency red light that we can see. If molecules in the sky scattered orange light instead of blue light, sunsets would be orange, yellow, green, or blue. And it would be the opposite, sunsets would be blue. So the colors listed, blue is closest to being the complementary color of orange. Next up, we'll look at why clouds look white. And clouds are essentially just clusters of various size water droplets. Now the size of the clusters of water particles depends or determines the scattered cloud color. So tiny clusters produce small bluish clouds, slightly large clusters produce greenish clouds, and larger clusters produce reddish clouds. The overall result is white clouds. Slightly larger clusters produce a deep gray, and still larger clusters produce raindrops. And lastly here, we'll look at why water is greenish blue. So water molecules resonate somewhat in the visible red which causes red light to be a little more strongly absorbed in water than blue light. Red light is reduced to 1/4 of its initial brightness by 15 meters of water. There's very little red light in the sunlight that penetrates below 30 meters of water. When the red is removed from the white light, the complementary color of red remains a cyan, a bluish green color. Our last example here looks at why we see this really pretty greenish blue color in this lake in the Canadian Rockies. And these lakes are fed by runoff from melting glaciers that contain fine particles of silt called rock flour, and these remain suspended in the water. And light will scatter from these tiny particles and give the water its really vivid bluish greenish color. And that is the end of our week 4 lecture, and I will be in touch with you again in week 5.